This is where we're going to stop today. All right. Now let's just take it. I'm going to write down the mass. Oh, that's a crappy pen. I'm throwing that one away. All right, let me write down all the information first. Mass is equal to 1.8 times 10 to the negative 5 kilograms. And Q on the charge is equal to positive 3.0 times 10 to the negative 5 coulombs. And the change in potential is equal to 25 volts. That's the change in potential. Okay. The only force is the positive force. All right, so let's just draw. Let's take a look at it, draw it. Here we go. So we've got this. It's a point A here. And then we're going to, and it's a positive charge. Okay. And if the potential down here at point B, if the potential down here is B is 25 volts less, then which way is the electric field going? It's losing potential, so there's a bunch of positive charge over here because there's a bunch of negative charge over here is what's going on. All right, so it's losing potential, but it wants to go that way. The electric field is pushing it this way. All right, and it's going through a positive distance. ED is positive. That's a positive distance that it's going. Okay, so the force and the change in X are both going in the same direction. So therefore, work is positive. If the work is positive, then what that means is there's a positive change in kinetic energy. Which means, so work is positive, so that means there's a positive, which means there's a negative change in potential energy, in the electric potential energy. All right? So that works. Okay? So the work done from A to B is positive. And here's what it equals. Here's what it equals. We've got Q, 3.0 times 10 to the negative 5 coulombs times the change in potential, which is 25 volts, which is negative 25 volts. So therefore, the change in potential is negative 25. So therefore, I've got a negative 75 times 10 to the negative 5 joules. And my change in electric potential, my change in potential energy, which is equal to a positive, so the work done is equal to a positive 75 times 10 to the negative 5 joules, which will equal 1/2 mv squared, which is the kinetic energy, the change in kinetic energy. Okay? Cool beans. And then to figure out its speed, figure out how fast it's going, v, velocity, is equal to 2 times the work over the mass. And take square root of all that. So we plug all that in. I know we did some gymnastics right here. I know we did some gymnastics. I could have said 25 minus 0 and made it positive 25, but we're not following along with what's actually going on. The physics. Here's the physics of the whole thing. Okay? So it wanted to go that direction. The electric field, the only thing that was acting on it was the electric field. So it was getting pushed. It's going from a higher potential to a lower potential. Its potential energy there thus decreased because there was a positive charge. A negative charge going the other way is going to require some kind of different force. An outside force is going to have to push that up the hill. Unless, of course, it's going from, unless we change its position, change it, not put it here at position A close to the negative charge, but put it here at position B and make it go close to the positive charge. Okay? So let's just go ahead and put in that answer. And we get 2. I'll do it one more time too. 2 times 3 second e to the negative 5 times 25 divided by, what's its mass? 1.8. And I get, when I plug in all the numbers, I get about 9.13 meters per second. Now, let's look at the negative charge. Let's say it's the same mass, same potential, but I'm going to put the negative charge here at B. I'm going to put a negative 3 coulombs charge there at B. So what's going on here? So at negative B, so at B, I'm putting a negative 3.0 times 10 to the negative 5 Coulomb charge here. Bunch of negative charge here because the potential difference is going to increase its potential difference as it goes to B, goes to A. So the electric field is actually pushing, in this case, the electric field is going this way from this negative thing. And so it wants to go from here to there. So its E field times D is equal to positive work. So positive work again leads to a positive kinetic energy, which will equal 1/2 m velocity squared. Same thing. But this is going from, like, say, negative 12.5 to positive 12.5. So it's still a negative change in voltage for this thing, because this is a higher voltage. So it's going like negative 12 minus 20. So it's going to be a negative voltage. So the change in electric potential energy is equal to Q, which is negative 3.0 times 10 to the negative 5. Now, remember, this one is higher. This is 25. Say this is positive 25 and this is 0. Then as I go from B to A, it's going to be 25. It's going to be VA minus VB. The change in voltage will be VA, because it's going from B to A. It's just like change in displacement. X final minus X initial. V final minus V initial would be negative 25 or positive 25, because it's going 25 minus 0. So once again, I wind up with this negative 75 times 10 to the negative 5th joules. So my electric potential energy is negative. So I make it my positive potential energy, 75 times 10 to the negative 5th joules, is equal to, this is the work done, is equal to the 1/2 times the m times v squared. And it'll be the velocity come out the same, 9.1, whatever we had, 3 meters per second from before. All right. Let's take a look, see what the slide actually says. 9.1. Oh, well, they're just going VA to VB. I didn't like that so much. I liked my explanation better because I like going X final minus X initial, but that's okay. It goes from A to B, 25 minus VB. That's the way they want to subtract the voltage, and it works okay. All right, so we'll stop there. It's a good place to stop.